Welcome to the deep dive. Today, we're really digging into Neuralink's Blindsight technology.
Yeah, exciting stuff.
You've been looking into this, brought some great material, including some Google AI insights.
That's right.
So the plan today is to really get to grips with what Blindsight actually is, then explore how it might, evolve, get better.
Especially that hybrid idea we talked about.
Exactly, the hybrid approach using non-invasive stimulation. That feels key. And then maybe zoom out a bit, think about wider uses beyond just sight restoration.
That's like a plan. We've got the details on the Blindsight device itself, the implant, the camera signals, stimulating the visual cortex.
Right, trying to give blind people some form of vision.
Yeah, and we know the first results are expected to be, let's say, basic, low res, but the long-term goals are, well, ambitious. Superhuman vision even.
We'll see about that. You also brought some thoughts on neuron entanglement, cross-brain region firing.
Just some ideas floating around, could be relevant later. And we've got that background info on what causes blindness globally, just for context.
Good, good. So a lot to unpack. Let's dive in. First things first, Neuralink's Blindsight. What is it exactly?
Okay, so at its heart, Blindsight is a BCI, right? A brain-computer interface, an implant.
From Neuralink.
From Neuralink, yeah. And the main goal is to restore some level of visual perception for people who are blind.
Even if they've been blind since birth.
That's the aim. And what's really different here is it targets the visual cortex directly, the part of the brain that handles sight.
So it skips the eyes, the optic nerve, all that.
Completely bypasses them, which is, a big difference from things like retinal implants that need the eye to still have some function.
Okay. And the FDA gave it that breakthrough status.
They did, yeah, back in September 2024, which really highlights its potential, shows how important it could be for a real medical need.
So this implant, it's coin size, you said? The Link. How does it actually create vision without eye input?
Right, the Link. It's about the size of a coin, goes into the skull surgically, and it has these thousands of electrodes. Super, super thin threads.
How thin are we talking?
Like 4 to 6 micrometers. Really fine. And they get inserted right into the visual cortex.
Wow. Okay. And the visual info, where does that come from?
From an external camera. Probably, built into glasses or some kind of headset.
Makes sense.
So the camera sees the world. A processor converts that into electrical signals.
And sends those to the implant?
Exactly.
Oh.
The signals go to those electrodes in the visual cortex. And by stimulating specific brain cells, specific neurons, it creates these patterns of light spots.
Phosphenes.
Phosphenes,
Yeah.
like little dots of light.
Pretty much. And the core idea, the hope, is that the brain, because it's so adaptable, neuroplasticity, will learn over time to interpret these patterns as vision.
Like pixels on a screen, but inside your head?
Sort of, yeah. But it's patterns of brain activity, not just pixels lighting up.
Okay. And the initial vision quality, you said low res?
Yeah, very low res initially. They've compared it to like old Atari graphics or really early video games.
Blocky and monochrome.
Yeah.
Black and white. Probably something like that, yeah. Blocky shapes. Not much detail or color. And that's mainly because of the number of electrodes.
How many are we talking?
Around 1,000, maybe 1,500 in the current plants, which sounds like a lot, and it's a big technical achievement. But the visual cortex has millions, maybe billions of neurons. So it's like trying to watch a 4K movie on a really, really old TV screen. You just don't have enough pixels.
Right. So the first step isn't perfect sight. It's just establishing that the brain can learn this new language.
Exactly. Can the brain adapt? Can it make sense of these artificial signals at all?
Yeah.
That's the first hurdle.
And even for someone blind from birth, the idea is that their brain can still learn this. That's pretty amazing if it works.
It is. The theory is basically that even without visual experience, the visual cortex structure is still there. It still has the underlying machinery to process visual info.
Even if it never developed normally.
Right. The usual pathways didn't form. But the hope is, with this consistent stimulation, this learning process, the brain can build new pathways, learn to interpret these signals as some form of sight.
Though it might feel very different from natural sight, I guess.
Oh, almost certainly.
Yeah.
We don't really know what that subjective experience would be like. It could be completely different.
So where are they with development? Have they started human trials for Blindsight yet?
Well, they've reported promising results from animal trials. Monkeys, mostly.
Musk said they were okay. The animal.
Yeah, he stated the implants worked as planned, animals stayed healthy, and after getting FDA approval for their earlier BCI trials, the ones for paralysis.
Right, the telepathy implant.
Yeah. So based on that, they've suggested the first human Blindsight implant could happen maybe late 2025,
Okay, so potentially quite soon.
potentially.
Hmm.
But, experts in the field are urging caution. They stress the initial vision will likely be very basic,
And the superhuman vision claims.
highly speculative right now. It's crucial to remember how complex the brain is. Just jamming in more electrodes doesn't automatically mean better vision. Neurons aren't just pixels.
Right, it's not a simple numbers game. Okay, so starting point. 8-bit graphics, basically.
Something like that, yeah.
Now let's talk improvements. Moving beyond that, you mentioned the hybrid approach. How could we get from Atari graphics to something like clear 2020 vision?
Okay, yeah, that's the big question. Getting from that basic output to sharp 2020 vision,
Yeah.
it's complicated. It'll need multiple steps.
More electrodes, better algorithms.
Definitely.
Yeah.
Higher electrode density, smarter algorithms to control the stimulation, those are essential. But there are limits to just the invasive implant on its own.
Which is where the hybrid idea fits in.
Exactly. This is where it gets really interesting, I think. Instead of only relying on the implant, we could combine it with non-invasive techniques.
Like the TMS and TES you mentioned.
Right. Transcranial magnetic stimulation TMS and transcranial electrical stimulation TES.
So pair the Neuralink precision with something broader.
Precisely. You get the implant's targeted stimulation in the visual cortex, but then you use TMS or TES to kind of shape how the rest of the brain helps process that information. It's about interpretation, not just input.
Okay, break that down a bit more. How would TMS or TES actually work with the implant to make vision better?
Think of it like this. Neuralink gives you that super precise, localized signal in the visual cortex. TMS and TES, working from outside the skull, can influence bigger areas, even distant ones.
Oh.
Well, TMS uses magnetic fields, right? They pass through the skull and create tiny electrical currents in the brain tissue underneath. TES uses weak electrical currents directly through electrodes on the scalp.
And you can target specific regions with these?
Yeah, you can target areas like, say, the parietal cortex that's involved in spatial awareness, understanding where things are, or the prefrontal cortex for attention focus.
So you could use TMS or TES to kind of boost those related areas while the implant stimulates the visual part.
That's the idea. The beauty of the hybrid approach is combining the implant's fine-tuned precision with the broader reach of TMSTs.
So the imprint makes the pixels, and TMS-TES helps the brain assemble the picture and understand it better.
Exactly. You modulate the parietal cortex, maybe the person gets a better sense of depth or layout from the phosphenes. You nudge the prefrontal cortex, maybe they can focus better on the new visual input, learn faster.
Ah, I see. It's about better integration across brain networks.
Right. Making the whole experience more coherent, more meaningful, and hopefully clearer than just the implant alone could manage.
Okay, that makes sense. Now, why is this better than, say, just using EEG? Isn't that non-invasive too?
Good question. EEG electroencephalography is mostly for recording brain activity, measuring the electrical signals from the scalp.
So it listens, it doesn't talk back?
Pretty much. It's incredibly useful for seeing what the brain is doing, understanding brain states, but it doesn't really change brain activity in the way TMS or TE can.
Ah, so TMS-TEs actively modulate or influence the neurons?
Correct. They alter the excitability of neurons, making them more or less likely to fire. EEG just observes. The hybrid approach is about active intervention to optimize processing, not just watching it happen.
Got it. Okay, so hybrid approach gets us potentially closer to 2020. What about the next leap? That superhuman vision idea, seeing infrared, UV, zoom vision.
Right. Superhuman. Exceeding normal human sight, that would definitely need more than just refining the current setup.
New sensors, I guess.
For sure, you'd need external sensors, cameras, or other devices that can actually detect infrared or ultraviolet or whatever extra information you want.
And then the implant has to translate that into brain signals.
Exactly. And not just translate it, but translate it in a way the brain can eventually learn to interpret as that specific type of information. That's a huge neural encoding challenge.
And how does the hybrid approach help there, with learning completely new kinds of input?
It could be crucial. TMS or TES could potentially be used to boost neuroplasticity even further, make the relevant brain areas more, well, malleable, more receptive to learning these totally new visual languages.
Priming the brain for unusual input.
Sort of, yeah.
Yeah.
And also potentially directing attention. When you're trying to learn to interpret, say, infrared heat signatures as vision, you need intense focus. TMSTs might help guide that attentional process during training.
So the implant delivers the weird new data, and the non-invasive part helps the brain actually learn to make sense of it.
That's the potential synergy, yes. It helps get around the limits of just adding electrodes. It allows for more iterative progress, maybe, and it works together with other advances like AI for encoding, better
It
sensors.
gives you more levers to pull,
Oh, yeah,
basically.
exactly. More flexibility, broader influence than just the invasive implant alone.
This is really compelling stuff, and it makes me think, if this hybrid approach works for vision, could we use the same basic idea for other neurological problems, or even psychological ones?
That's a great question. And yeah, your intuition there is spot on, I think.
Really?
Yeah, the core principles, the precise invasive targeting combined with broader non-invasive modulation, aiming for synchronized activity, leveraging plasticity, those seem quite adaptable.
So the same kind of toolkit for different issues.
Potentially, yes. The basic idea of pinpointing a dysfunctional network or node with the implant and then using TMSUD to help rebalance the wider system that could apply elsewhere.
Like what? Give me some examples.
Okay, take speech loss.
Yeah.
Say, after a stroke, someone damages language areas or motor control for speech.
Okay.
An implant could go into those specific areas, maybe stimulate residual neurons, or even try to decode the intended speech directly from brain activity.
And the TMSCs.
Could target connected regions, maybe the corresponding area in the other brain hemisphere, or prefrontal areas involved in planning speech or attention. Synchronizing the implant stimulation with the TMSD modulation might help strengthen alternative pathways or help the brain compensate.
Interesting. What about something like chronic pain, neuropathy?
Right, neuropathic pain involves messed up signaling in pain pathways. An implant could potentially target key pain processing hubs, thalamus, maybe singulate cortex to try and dampen that aberrant activity.
And TMSECs.
Could be aimed at areas known to influence pain perception, like the dorsolateral prefrontal cortex, or even the motor cortex. Again, the idea is synchronized modulation to try and recalibrate those pain circuits.
Okay. Could this really stretch to mental health, like anxiety, schizophrenia? Those seem so complex.
They are incredibly complex, absolutely, but they also involve network dysfunctions. Take anxiety, often linked to an overactive amygdala, and poor regulation by the prefrontal cortex.
So implant in the amygdala or prefrontal?
Potentially target those to modulate the fear response, while TMSTCs applied to the prefrontal cortex could boost its regulatory control.
And schizophrenia.
Also involves disrupted connections, prefrontal, auditory cortex, other areas. An implant might target areas involved in hallucinations or cognitive issues, while TMSTs could modulate connected zones like the temporoparietal junction or prefrontal cortex to try and reduce symptoms. It's speculative, but the principle holds.
Wow. What about addiction? That's notoriously hard to treat.
Addiction involves the brain's reward circuitry going haywire, nucleus accumbens. Prefrontal cortex are key players. An implant could target these to modulate reward sensitivity or maybe boost impulse control.
With TMST's backup.
Yeah, TMST aimed at the prefrontal cortex again, or maybe the insula, which is linked to cravings. Synchronizing could help disrupt those craving signals and strengthen inhibitory control.
It's kind of mind-blowing that one core hybrid strategy could potentially touch on so many different conditions.
Well, it points to the underlying shared mechanisms, right? Many of these conditions involve disruptions in communication between specific brain regions and broader networks.
So it's about fixing the connections.
In a way, yes. Tailoring the precise invasive target and the non-invasive modulation to the specific network problem in each condition. And your interest in Neuralink probably taps into this huge potential, a technology that could interface with the brain on this fundamental level.
Okay, let's pivot slightly. Hearing loss. You touched on the auditory nerve and mental health links earlier, and we've got this info on current tech hearing aids, cochlear implants, BAAs. How could those existing technologies be integrated with Neuralink and this TMSDS hybrid approach?
Yeah, really important connection. Hearing loss isn't just about not hearing sounds. It impacts social connection, mood, even cognition.
Isolation, depression.
Exactly. So integrating what we already have with Neuralink and TMSTs, that's not just about better hearing. It's potentially about improving overall well-being, too. It's about optimizing how the brain uses sound.
Okay, so let's take them one by one. Standard hearing aids. How could Neuralink plus TMSDES help there?
All right, hearing aids amplify sound, right? Neuralink could potentially add a layer after the amplification. An implant in the auditory cortex could help refine how the brain processes those boosted sounds.
Like better speech understanding and noise, that's a big issue.
Precisely, fine-tuning the brain's interpretation. Maybe AI in the Neuralink system could even actively filter noise based on what the user's trying to focus on, judged by their brain activity.
And the TMSTA's part?
Could target prefrontal areas to enhance auditory attention, helping the user focus on the amplified sounds they want to hear, especially in complex environments.
Okay. What about cochlear implants? They already stimulate the auditory nerve directly.
Right. With cochlear implants, Neuralink could potentially interface with the implant electrodes or target the auditory cortex directly to refine those electrical signals.
For a richer sound, better music perception.
That's the hope. Maybe a more natural, nuanced sound quality. And TMSTDs could be really useful during the adaptation phase after someone gets a cochlear implant. Boosting plasticity could help them learn to interpret the new signals faster and better.
Makes sense. And BAHAs, bone-anchored systems.
BAHAs send sound through bone conduction. Again, Neuralink in the auditory cortex could enhance the brain's processing of those signals, improve clarity, maybe sound localization where sounds are coming from.
So especially for single-sided deafness.
Could be very helpful there, yeah. And TMSTs might target the auditory cortex on the other side of the brain or parietal areas to further boost that spatial hearing ability.
Lastly, ALDs, assistive listening devices.
Those are for specific situations like classrooms or meetings. Neuralink could maybe process the ALD signal directly, offering more sophisticated filtering or enhancement right in the brain. AI could help adapt the processing in real time. And TMSTs, again, maybe boosting auditory attention for those demanding situations.
So it seems like for all these existing techs, Neuralink plus TMSTES adds this layer of brain-level optimization and support.
That's a good way to put it. But you also asked about benefits beyond just hearing restoration.
Right. The mental health aspects, cognitive load.
Exactly. Because hearing connects to so much else. Improving it could directly reduce the social isolation linked to hearing loss. TMSTs could even offer direct mood modulation if needed.
Less brain effort spent just trying to hear.
Potentially, yes. Reducing that cognitive load might free up resources, potentially helping memory, attention, and then there's sensory augmentation.
Like hearing things that aren't sound.
Maybe integrating other data streams via the auditory cortex. And we touched on links to other conditions maybe influencing schizophrenia or addiction via auditory pathways. And way out there, brain-to-brain auditory communication.
Telepathy again. Okay, this is all building towards something. This feels like a eureka moment brewing.
Oh.
Yeah, it seems like this combination, TMSDS, which kind of evolved from my initial thought about EEG, right?
Right, the active modulation versus passive recording.
Yes. That, combined with not just one Neuralink implant, but maybe multiple implants placed strategically, that feels like the real game changer here. A way to maybe accelerate this whole field, but safely.
Ah, I see where you're going. That combination. PMSTS plus multiple strategically placed implants.
Yeah.
Yes, that is a potentially powerful synergy. It could indeed be a way to accelerate things significantly.
Okay, unpack that. Why is that specific combination such a big deal?
Well, first, as we said, TMSTs gives you that non-invasive broader network influence, going beyond just recording like EEG.
Check.
Second, multiple implants. Not just jamming more electrodes in one spot, but placing implants in different connected key regions. Visual and parietal cortex, maybe? Auditory and prefrontal.
So you can directly stimulate and coordinate activity between important hubs.
Exactly. You can enhance the brain's own functional connectivity in a targeted way without needing one single, super dense, incredibly complex implant. It's targeted influence across a network.
Seems more elegant, more efficient.
Potentially, yes. And that synergy could be a real accelerator. Why? Because the TMSTEs might help the brain make better use of fewer implanted electrodes initially. It primes the network.
So you don't need the absolute cutting edge in electrode tech right away.
Maybe not. It could also enhance plasticity like we discussed. Faster adaptation, shorter training times, and because this combined approach is potentially applicable to many conditions.
Research and development could be streamlined. Learnings from one area apply to others.
Precisely. A more unified platform approach.
But safety, multiple implants sounds riskier. And TMSTs isn't risk-free either.
Absolutely critical point. Safety is paramount. Multiple implants do mean more surgery, but strategic placement, guided by imaging, plus Neuralink's robotic surgery aims to minimize risks.
Precision helps.
And for TMSTEs, there are established safety protocols. Plus, imagine having the implants monitoring brain activity in real time. You could potentially use that data to dynamically adjust the TMSTS stimulation, keeping it within safe limits, preventing side effects.
Closed-loop safety system, almost.
Could be. And of course, rigorous phase clinical trials are non-negotiable. Start small, focus on safety, then scale up to test efficacy. AI would also be huge for monitoring the vast amounts of neural data for any warning signs.
Okay, so this hybrid multi-implant approach, it really could be a unifying strategy for tackling brain disorders.
It feels like it has that potential. The same basic hardware-software framework adapted for vision, hearing, mood, movement, using implants for precision and TMSDEs for network tuning.
Streamlining development, maybe costs down the line.
Could be. And it opens doors to those more advanced things, sensory augmentation, maybe even that telepathic communication idea you had.
And quantum AI eventually optimizing the whole complex dance.
Who knows?
Yeah.
Further down the line, perhaps. But the core idea is that this combined approach accelerates things. Faster iteration, broader impact, maybe safer scaling by integrating with existing tech first.
Right. It makes the path forward seem clearer, maybe more achievable sooner.
It leverages multiple strengths, invasive precision, non-invasive reach, coordinated multi-site action. It's a compelling vision, definitely.
Okay, this has been, well, a really fantastic deep dive. Let's try and sum up the key takeaways. We started with Neuralink's Blindsight, how it works by stimulating the visual cortex.
Right, bypassing the eyes, starting with low-res phosphene vision.
Then we explored how a hybrid approach, combining that implant with non-invasive TMS or TES, could potentially enhance vision first towards 20/20, maybe even superhuman capabilities eventually.
By modulating broader brain networks to help process the implant signals and adapt to new inputs.
And we saw how that same hybrid principle, precise implant plus broad modulation, could apply to a whole range of other conditions: speech loss, pain, anxiety, addiction.
Targeting the specific dysfunctional networks involved in each case.
Then we looked at hearing loss, integrating Neuralink and TMS-TS with existing tech like hearing aids and cochlear implants.
Not just restoring hearing, but potentially boosting mental well-being and cognitive function too.
And finally, that Eureka idea, using TMS-TS alongside multiple strategically placed Neuralink devices.
As a potential game changer to safely accelerate development, enhance plasticity, and create a more unified platform for neurotechnology.
It really feels like this convergence of invasive and non-invasive tech, precision, and broad influence is a powerful path forward.
Agreed. The synergy seems to overcome limitations of focusing on just one method. It's a very promising direction.
So thinking about all this, the convergence, the potential for sensory augmentation, maybe even brain-to-brain communication down the line, what ethical or societal questions jump out to you as the most critical ones we need to grapple with as this stuff moves from the lab into the real world?
That's a big one.
Yeah, I mean, what safeguards do we need, especially around things like fair access, preventing misuse as we start, literally remixing our senses with technology? What should we be thinking about now?